Okay, let's continue the talk on Introduction to Probability with the idea of independence. So, we talk about independence in events all the time, but it actually has a specific statistical meaning. Two events are defined as independent if the probability of A given B is the same as the probability of A, if the probability of B given A is the same as the probability of B, and if the probability of A and B is the same as the product of the two probabilities. So let's break down what that actually means in layman's terms. What we're saying is the probability of something happening given that something else has happened. The probability of getting an A given that you are female is the same as your probability of getting an A. That being female does not actually impact your probability. Or if the probability of being female given that you have an A is the same as the probability of being female. What we want to know is that the conditional doesn't change the outcome, that event A is independent of event B. And mathematically, the way that will shake out is that the probability that both things are true will be equal to the product of the probabilities. When we talk about independence, we need to talk about two kinds of sampling for independence. The first is the idea of sampling with replacement. And when we sample with replacement, it means we pull something from the set and then we put it back before we draw again. That would be like using a deck of cards. If you pull out the ace of hearts, you would put it back in the deck, shuffle again, and then pull cards again. If you pull without replacement, that would mean that you pull the deck, take your deck of cards, pull the ace of hearts, put the ace of hearts aside, and then pick from the remaining 51 cards. In the case of without replacement, if we've removed the ace of hearts from the deck, we have changed the likelihood of picking an ace the next time. Sampling with replacement is independent. Sampling without replacement is not. Now, in certain situations, we are going to consider sampling without replacement to be basically independent. That is, if there are 10,000 things in our sample size, removing one thing is not going to completely change the outcome. But we will talk about that more when we get to large-scale sampling. The other concept we need to talk about is the concept of being mutually exclusive. Now, mutually exclusive means that two events cannot happen at the same time. And you saw this in the last video with things like, can a number be even and odd at the same time? Being even and being odd are two mutually exclusive events. There is no overlap. There is no situation in which a number can be even and odd. So say we draw two cards from a standard 52-card deck with replacement. Find the probability of getting at least one black card. So how would we find that probability? We would, what's the probability that the first one is black? Remember that 1/2 of the cards is black and 1/2 of the cards is red. So we have a 1 in 2 chance of picking a black card. Okay, so let's consider the 4 possibilities. They can be one of 4 things. We could pick a black and a black. We could pick a red and a black. We could pick a black and then a red, or we could pick 2 red cards. So, the likelihood of getting at least one black card would consider this case, and this case, and this case. So 3 out of 4 possibilities of getting at least one black card. And in those possibilities, all of them are equally likely because the probability of getting a black card and the probability of getting a red card are the same. Now, if I consider to find the probability of getting at least one club, that would be a different animal. So in this case, because being black and red are mutually exclusive, the probability is going to be 3 out of 4. So let's try this one. We're going to flip 2 fair coins. And 2 fair coins mean the possibility of getting heads is equal to the possibility of getting tails. So we're going to let A equal getting at least 1 tail, B getting all tails, C getting all heads, D getting more than 1 tail, and E the event of getting head on the first roll. So let's talk about the sample space. So if we're flipping 2 coins, we could get heads, then tails. We could get heads, then heads. We could get tails, then heads. Or we can get tails and tails. And because they're fair coins, these are all equally likely. Okay? So, let's figure out the probability of A. The probability of getting at least 1 tail is going to be this one, and this one, and this one. In this case, it would be 3 out of 4, which is 0.75. So the probability of B getting all tails is 1 out of 4. It's 0.25. Probability C of getting all heads is again 1 out of 4. 0.25. The event of getting more than 1 tail, it'd be the same as getting all tails. 1 out of 4, which is 0.25. And the event of getting a head on the first roll is this situation and that situation, so it'll be 2 out of 4, which is 0.50. So let's try one more example. Try at 3.13, which in the OpenStax book is page 177. We consider a box that has 1 white ball and 1 red ball. And we're going to select a ball, put it back in the box, and select again with replacement. So let's consider our sample space. We're going to do it twice. We can either get red and red, red and white, white and red, white and white. This is very similar to the coin flip example. So let T be the event of getting the white ball twice. Since they're mutually exclusive and they're both equally likely, there's only one situation where we get the white ball twice. So that will be 1 out of 4, which is 0.25. So how about we compute the probability of getting the white ball twice, given that we've already picked one? So remember that to find conditional probabilities, we're going to find the probability of both divided by the probability of the second. So that will be the probability of both is 1/4 divided by the probability of the second. And the second one, remember, is picking the white ball first. That happened twice. So this will be 1/4 divided by 1/2, which is 1/2. So the answer to this one is 0.50. Are T and F independent? So there's the question. Does the probability of T given F equal the probability of T? And the answer is no. Because do you see P of T is 0.25 and PT given F is 0.5? Are they mutually exclusive? Can we pick, remember F is the event of picking a white ball first, and S the event of picking the white ball second. Can we pick the white ball first and the white ball second at the same time? Yes, we can, and that situation is right here. So no, they are not mutually exclusive. Are F and S independent? So again, what's the probability of F given S is the probability that we've picked a white ball first, given that we picked a white ball second. So that's going to be the probability of F and S. My pen's not writing very well. divided by the probability of S. So over here, I'm going to do it up here a little bit. So the probability of F and S, picking a white ball first and second, is 1 out of 4. And the probability of picking a white ball second is 2 out of 4. So that's going to be 1/2. So then the question is, what's the probability of picking a white ball second? And that is also 1/2. So yes, they are independent. Okay, we're going to do a lot more of these kind of problems, and probably the most complicated things we'll do concern conditional probability. So go through and read the end of this chapter, the end of chapter 3, and we will talk about this more in class this week. If you have any questions, let me know.